In today's video, we'll learn about the conservation of momentum. Conservation of momentum states that when a collision occurs in an isolated system, the total momentum of the system doesn't change with the passage of time. Instead, it remains constant both in magnitude and direction, which means that the vector sum of all the momenta will not change, and that the total momentum is therefore said to be conserved. And according to Newton's third law, it states that all times these two forces is equal in magnitude and opposite in direction. And since these factors act over the same time interval, we can get the equation where the force of object 2 acting on object 1 is equal but in opposite direction of the force of object 1 acting on object 2. And when we expand these two forces over a time period, we can see that the change of momentum is equal in magnitude but opposite in direction. If we rearrange this equation, we get mass times the final velocity of object 1 plus the mass times the final velocity of object 2 is equal to the mass times the initial velocity of object 1 plus mass times the initial velocity of object 2. And our first example states that a bullet shown in the picture collides to a fixed block. So the interaction time of the bullet with the block is 0.2 seconds. If the velocity of the bullet is 250 meters per second after the collision, find the resistance of the block to the bullet. We can first start by summarizing the information that is given to us. From the picture, we can see that the mass of the bullet is 200 grams, or if we convert it to kilograms, would be 0.2 kilograms, and that the initial velocity of the bullet is 500 meters per second, and the final velocity of the bullet is 250 meters per second. Well, the mass, which we'll define with the subscript of 2, has a mass of 8 kilograms, an initial velocity of 0 meters per second, and a final velocity of 0 meters per second. So what we're trying to find is the force lost due to the bullet and the block colliding. If we apply our conservational momentum equation, which states that the mass of the bullet times the final velocity of the bullet plus the mass of the block times its final velocity is equal to the mass of the bullet times its initial velocity of the bullet plus the mass of the block times the initial velocity of the block. So since our block has a final velocity of 0, this part of the equation will equal 0, as well as the initial velocity of the block is also 0. So this part of the equation will also be 0. If we subtract the mass of the bullet times its initial velocity of the bullet from both sides, where we'll have the mass of the bullet times its final velocity minus the mass of the bullet times its initial velocity. And from this equation, this is equal to having the final momentum minus the initial momentum. So we see that our final momentum minus our initial momentum is the same as having our change in momentum is equal to the mass of the bullet times its final velocity minus the mass of the bullet times its initial velocity. And if we plug these values in, we'll see mass of the bullet 0.2 kilograms times the final velocity of the bullet, which was 250 meters per second, minus the mass of the bullet times its initial velocity of 500 meters per second. We see that the change in the momentum is equal to 50 minus 100. So our change in momentum is a negative 50 kilograms times meters over seconds. Since we know our change of momentum, we know that the change of momentum is also equal to the average force times our change in time. We can rearrange the equation to solve for the average force, and when we do so, we see that the average force is equal to our change in momentum over our change in time. If we plug in our values, we can solve for the average force that the block exerted on the bullet. So our change of momentum was 50 kilograms times meters per second divided by a total time of 0.2 seconds. And when we do so, we see that the average force that the block exerted on the bullet was a negative 250 newtons of force. In our second example, it states that two cars are stationary at the beginning. If the car has a mass of 100 kilograms and starts to move to the east with a velocity of 5 meters per second, find the velocity of the car that has a mass of 4 kilograms with respect to the ground. So if we start by summarizing the information, we see that the mass of cart 1 is equal to 4 kilograms. Its initial velocity is 0 meters per second, and its final velocity is unknown. And for our second mass, it has a mass of 10 kilograms, an initial velocity, also 0 meters per second, and a final velocity of 5 meters per second. If we use the conservation of momentum equation, we'll have mass of block 1 times its final velocity plus the mass of block 2 times its final velocity equal to the mass of block 1 times its initial velocity plus mass 2 times its initial velocity. Since both our velocities for both our blocks are 0, we'll see that 0 times whatever the mass is will equal 0. If we rewrite our equation and plug in our values, we'll see that the mass of block 1 is 4 kilograms. The final velocity of block 1 is unknown, plus the mass of block 2, which is 10 kilograms, times its final velocity of 5 meters per second, is equal to 0. And then we can see that we can get our final velocity by itself if we subtract the mass of block 2 times its final velocity and divide by the mass of block 1. We can solve for our final velocity. And when we do so, we'll see that our final velocity is equal to a negative 12.5 meters per second. And since our velocity is negative, that must mean that the direction of our velocity is towards the negative x-axis, which would mean that the mass of block 1 is traveling in the west direction.